Hello and welcome to Maths on the Move, the podcast from plus.maths.org. My name is Marianne Freiberger. In last week's episode of Maths on the Move, called Telescope Topology, we explored a result in pure mathematics that was all about exploring what happens in higher dimensions. Now, this reminded us of a podcast we recorded back in 2012 as part of our science fiction science fact project, where we talked about higher dimension with a theoretical physicist, David Berman. David told us that in one sense we're all very used to thinking in higher dimensions and even thinking about living in a curved universe. But when it comes to theoretical physics, the idea of these extra dimensions take on a whole new significance, and things get very interesting indeed. Here is my colleague Rachel Thomas talking to David at a very busy Centre for Mathematical Sciences in Cambridge back in 2012. She started off by asking him if there are more dimensions than the 3 dimensions of space that we perceive.
Well, there's definitely more, and you can see one of them at least, and you're very familiar one, which is time. So let's think a bit about what we mean by dimensions. If we live in 3 dimensions, it's the ways that we can move. But let's think about what it means in terms of giving someone an address. So what you normally do is you basically tell them where you are, and in doing that you specify normally where you are in 2 dimensions. So you give an address, and if it's New York, it's great. It's 35th and 56th Street. It's like how many blocks north and how many blocks east-west, right? So then that's simple 2-dimensional address. But then New York's another good example. You can be high up or low down, and you've got to give what floor you're on. So you're on the 5th floor, so that's 3 coordinates, 3 things that you specified: how far north and south, how far east and west, and how far up. But then supposing you were not telling someone what your address is, but you're arranging a meeting. So then you realise, well, you need to give one more thing, which is the time of the meeting. Say 3 o'clock. And so then you realise you've got 4 coordinates which describe any point for an event or a meeting or something. And so really we are used to living in 4 dimensions, where the 4th dimension is time. And so that's the first thing. It's just that we don't tend to clump time with the other spatial things. But if you think about it, any event at all really happens in a space-time with 4 dimensions.
And essentially because you can say where you are in terms of the time dimension. You might not be able to go forwards and backwards in time like you can go left and right, but you can specify where you are.
Yeah, exactly. And we measure differences in time just like we measure differences in space. We measure differences in space with a ruler. We measure differences in time with a clock. Mm-hmm. So anything that you can think of in terms of space, you can also think of in terms of time.
So 4 dimensions is enough?
So 4 dimensions of space-time is certainly one thing, but there's a sort of lesson to have from this, that our human perceptions of dimension is limited because we only see those 3. We don't see time in the same way. We experience it very differently as human beings. So but in what I've described, and I think people can see, time is an extra dimension, it's an extra location for any event, that it hints at human perceptions of things may not be the end of the story in terms of what's possible. So mathematically, the number of dimensions is really just the number of coordinates you need to give to specify a point somewhere. So it's easy to mathematically say, I can imagine a space where I need 5 bits of information, 5 measurements that will specify. That'll be a 5-dimensional space, or 6 or 7. There's no limit.
And mathematicians regularly work in arbitrarily many dimensions, don't they?
Absolutely. And, in a weird way, we all do when you think of other sorts of things. So, for example, if you're a sound mixer making music, then you can have 12, 24, 128 tracks, and they have a volume on each one. So that's really, and the volume of each one is saying how loud each one of those tracks are going to be, and then it mixes it together. So that's, if you like, pointing out, it's changing a point in that, whatever it is, 24-dimensional space of sound as they move it. So really a dimension is just, or a set of dimensions is just a way of specifying a point, and it's the number of bits of data that you need to give that point. Now, physically, physicists historically have looked at whether it's possible to consider more than 3 spatial dimensions. So Einstein combined space with time, and that we've already spoken about. But then some other people had the idea, in particular 2 people called Kaluza-Klein, who were very shortly after Einstein, had the idea that it's worth thinking about whether the number of spatial dimensions could be bigger than 3. And they had the idea in the following way. General relativity, which was Einstein's big idea, said that dimensions could be curved. Now, we're used to that as well. We spoke about a 2-dimensional thing, but think of the surface of the Earth. That's 2-dimensional, and it's curved, and so we specify longitude and latitude, but indeed you sort of come back to yourself. The coordinates are periodic, so you can go 360 degrees round the Earth. And that's fine. That's a 2-dimensional surface inside 3-dimensional space. But they said, well, if we can have real space, physical space itself curved, couldn't it be curved like the surface of the Earth, or like a circle, so that you can come back on yourself? So the dimensions don't go on forever, as we imagine off in space, just go on forever. But there could be just space, this dimension of space itself could be curved, and it could be curved so much that it comes back on itself like a circle. Well, you think, well, that sounds good, a bit weird. You'd sort of go off in space in your rocket ship and then come back on yourself. And so that doesn't seem likely. And why wouldn't we see these dimensions? But then you think, well, how big can the circle be? And what if the circle was, say, 100th, 1,000th the size of an atom? Well, that's so small, you wouldn't notice so much. And this is like, when I'm giving an address in 2 dimensions, if my house is 1 step up, I don't normally specify that, because it won't really be noticed. If they're travelling 3 miles one way, 1 mile another way, you don't go, and then you come to the house and it's 1 centimetre above the ground because of some tiny step. It's irrelevant to the big picture of wherever. So the idea of Kaluza-Klein is that you could have extra dimensions. They had 1 extra dimension, but that dimension will be curled up into a circle, and the radius of that circle will be so small, it'd be smaller than any other scale that was around, so you wouldn't notice it. Now, then you start to get into things. Well, why introduce it in the first place if you can never notice it? So they showed, using general relativity, that it still had an effect in the ordinary space around us. And in particular, the effect is that gravity in that 5-dimensional space-time looked like, from the effective, the people who are big and really only saw 3 space and 1 time dimension, the effect of gravity in that extra dimension actually looked like electromagnetism. So we see gravity and electromagnetism in our space, and what Kaluza-Klein sort of showed is that actually it could be just gravity in 5 dimensions, where the 5th dimension is very small, and what we see as being electromagnetism is actually the effect of 5-dimensional gravity. And then little things like the radius of this extra dimension was related to the electric charge. And that charge quantization, which we see in the universe, is a consequence of, sort of combining quantum mechanics with this, and the quantization of momentum of things moving in that extra dimension. So in other words, things that are charged under electromagnetism in this Kaluza-Klein version are just things that are moving in the 5th direction.
So going around the very tightly curled...
Yeah, going around that circle. So you don't see them move in our dimensions, but they're moving there. And then you can ask yourself how a charge and anti-charge produces a neutral thing, because you've got one thing moving one way, one thing moving the other way, and then when they hit, their momentum cancels, and then they don't move anymore in that direction, and then they're neutral.
So was that accepted? That
people thought they were mad. Einstein discouraged them from publishing. It just seemed remarkable. I mean, it was a mathematical oddity. It was mathematically true, but it seemed very strange. So there was certainly nothing forbidding it, though.
So we potentially have 4-dimensional space and one dimension with an extra dimension of time, making 5.
So that was in the 1920s, and the idea was looked at quite seriously. And it had the advantage that it seemed to unify electromagnetism and gravity into one thing. But then people saw there were more forces in nature than electromagnetism, and they wanted to unify that, and they tried that, and that got somewhere, but that needed more dimensions. And then, along came string theory in the 1980s. String theory was a bit before then, but in the 1980s it became realized as a quantum theory of gravity. And it had one very unique thing which no theory before has ever had, which it predicts the number of dimensions of space and time. And in the superstring theory it says the answer is 10. Now, some people have taken this to be a criticism of string theory, because if it predicts 10 and then they look around for space-time and they go, well, where are the other 6 dimensions? But then, of course, that just fitted in with this old Kaluza-Klein idea that, yes, there can be extra dimensions and they're small, and now we have a reason for why we should think that they're there, is that the mathematical consistency of string theory requires extra dimensions.
So could you give us a brief idea of what string theory is?
Okay, I'll tell you. String theory is just the idea that the fundamental building blocks of nature are string-like, not point-like. It's really that simple. Mm-hmm. But it has enormous consequences in terms of its consistency. And one of those consequences, it says, where these little bits of string live, has to have a certain number of dimensions. It doesn't require them to be curled up or not. That's not part of it. It just requires there to be a certain number of them. And then you've got a problem. String theory requires there to be a certain number. We observe only 3 spatial dimensions, therefore we need to solve that problem, and then you say, well, Kaluza and Klein already solved that problem, they curled them up. But string theory actually doesn't tell you at all why they're curled up. And that's one of the great puzzles of string theory.
So can you get evidence for string theory then how can you get evidence for the number of dimensions that string theory predicts then?
Can we ever observe extra dimensions? I assume by that you mean experimentally.
Yeah.
In principle, yes. In practice, it depends on how small they really are. And I'm not sure I can tell you how small they really are, because there could be various possibilities. So people at LHC have been looking for signatures of extra dimensions. So, in principle, yes. In practice, it depends on how small they really are.
what are the implications? What would a signature look like? What would the implication of an extra dimension be on our three-dimensional space that we might be able to see?
Well, there's some very simple things. So the forces between two charged objects or between two massive objects goes as famously the inverse square law. Newton did that. Between two gravitational bodies, F equals G_mm over r squared. Between two charged bodies, Q squared over 4 pi epsilon naught r squared. It's always like 1 over r squared. Right? That 1 over r squared is tied to 3 spatial dimensions. If you are in d dimensions, okay, then the force between two objects goes like, in d spatial dimensions, goes like d minus 1. So we're in 3 dimensions, it goes like r squared.
Right. Do you mean that you'd have r to the power of d minus 1?
Yeah.
Oh, okay.
Yeah, or 1 over it, obviously.
Yeah. So in 3 dimensions,
it's 1 over r squared. In 5 dimensions, well, let's see. It's always whether I'm including time in this is always what I'm doing. So I'm just including space dimensions. Mm-hmm. So in 9 dimensions, spatial dimensions, it'd be 1 over r to the 8.
Thanks.
So they have set up, they look for deviances from the 1 over r squared law. Now, it's very hard to do those sorts of experiments because the point is you should do them at distances which are incredibly small. So, because, that 1 over r to the d minus 1 is when the space is sort of flat and infinite dimensional. So then, when one of the dimensions is curled up, then when you're at separations bigger than the curled up dimensions, it looks like the dimension less. And when you're at things much smaller than that, then it looks like that law. And in between, it interpolates. If you see what I mean.
Yeah. I mean, it's like a transition.
You're transforming, say, from 1 over r squared to 1 over r to the 8. Yeah. And where that transition occurs is that scale. So you need to have things that are close. But yeah, in principle, forces will change as you approach that scale. And so even if you couldn't bring balances together and measure them, when you do scattering experiments, like they do at LHC at very high energies, then you could, in principle, because the forces of interaction are different, you could see different things.
That was David Berman talking to Rachel Thomas back in 2012. And although some time has passed since then, evidence for extra dimensions as predicted by string theory still hasn't been found. Thanks for listening and bye-bye.